Hi, I'm Ravindra Bandara from University of Auckland, and today I'm going to talk about infinitely many multipulse solitons of different types in a waveguide with quartic dispersion. Optical solitons have been the focus of many studies during the last few decades. In general, solitons exist due to the balance between the anomalous quadratic dispersion and Kerr nonlinearity. However, recently some solitons with new characteristics have been discovered. As you can see in this figure, generally solitons have exponentially decaying tails. However, they noticed that the soliton they discovered have oscillating tails, and they realized that unlike the conventional solitons they have discovered exist due to the balance between the anomalous quartic dispersion and kernel linearity. So somebody can have the question whether soliton exists in the presence of both quartic and quadratic dispersion. Therefore, first we introduce the generalized nonlinear Schrödinger equation, which is used as a model to describe the pulse propagation along a fiber in the presence of both quartic and quadratic dispersion. If you look at the literature, you can find many people who have worked on this problem. Initially, Carlson and Hooke found an analytical expression to the generalized nonlinear Schrödinger equation in the presence of both quartic and quadratic dispersion. However, this expression only able to describe solitons which has exponentially decaying tails. Later, this expression was rederived and they found that it is stable up to a threshold value of the third order dispersion too. They found that there exists soliton with oscillating tails. And however, they only able to find these oscillating tail solitons when beta 2 is negative. Recently, Kevin Tam found that these oscillating tails not only exist when beta 2 is negative, but for positive beta 2 values as well. So initially, we had few fundamental research questions. Are there different type of solitons exist beyond the one-harm soliton? If they exist, what is the mathematical mechanism that explain the existence of these solitons and in which parameter range they exist? In order to find answers for this question, we use bifurcation theory and continuation techniques. First of all, we use a traveling wave ansatz to transform the PDE into an ordinary differential equation, which has two mathematical properties. That is, the ODE is reversible and Hamiltonian. And I'm not going to move into much details of these mathematical properties. Furthermore, we can write down this ODE as a system of four first order ODEs. And we are going to use this system to find new soliton solutions of the PDE. A homoclinic orbit or a homoclinic solution is a trajectory of the ODE that converge both forward and backward in time to the same equilibria of the ODE. Therefore, finding new homoclinic orbits of the ODE is same as finding new solitons in the PDE. Therefore, from this moment onwards, you can consider any homoclinic orbit we are going to find as a soliton of the PDE. Here in this figure, we are showing a homoclinic orbit of our system for this given fixed parameter value. As you can see, first we are showing it as a u1 as a function of time. So you can see it start with the equilibrium 0 and reach a maximum value, and it's converge back to the equilibrium 0. And here we also show a 3D projection of the same homoclinic orbit. So in this panel A, we are showing how the eigenvalues of the equilibrium changes in beta 2 mu parameter plane. If you consider region 1, the equilibrium 0 has 4 distinct real eigenvalues. Therefore, in this region, the homoclinic orbits has exponentially decaying tails, as you can see in figure panel B. In region 2, equilibrium has complex conjugate eigenvalues, pair of complex conjugate eigenvalues. So in this parameter region, the homoclinic orbit has oscillating tails as in panel C. In region 3, the equilibrium has purely imaginary eigenvalues, and there does not exist any homoclinic orbits in this region. However, most interestingly, it was found that in fourth order reversible Hamiltonian system, in the parameter range where equilibrium 0 has complex conjugate eigenvalues, that is the region 2 in this diagram, we can find infinitely many symmetric homoclinic orbits with oscillating tails. So in this figure, the panel A, we are showing a E to P connection, or a connection between equilibrium 0 to the periodic orbit for this given fixed parameter value. Here the green color curve is the periodic orbit and the blue color curve is the connection from the equilibrium to the periodic orbit. So here we are interested in such connection because these connections are organized in centers for the existence of homoclinic orbits of our system. For an example, if you see panel B1 to B3 and C1 to C3, all these homoclinic orbits are associated with the E to P connection shown in panel A for this given fixed parameter value. Also, you can see that all these homoclinic solutions have a different number of humps. Therefore, we call this as multi-hump homoclinic solutions. Furthermore, since our system is reversible, we can find different type of homoclinic solutions which has different symmetries. For an example, if you consider panel B1 to B3, all these homoclinic solutions are symmetric, has symmetric temporal profiles. And if you consider panel C1 to C3, all these homoclinic solutions has antisymmetric temporal profiles. And the next question is, since all these homoclinic orbits for fixed parameter value, what will happen if we change one parameter value? Therefore, we fix the parameter values and we change beta 2 and obtain the bifurcation diagram of these homoclinic orbits as in figure D and figure E. Here, in both these bifurcation diagrams, our y-axis is the L2 norm of U1. Here, the black dash curve bounds the interval of beta 2 where equilibrium 0 has complex conjugate eigenvalues. The cyan color curve is the bifurcation diagram of the E to P connection. And if you look at the red color curve, that corresponds to the bifurcation curve of the primary homoclinic solution or the one-arm homoclinic solution which was previously found. It exists entirely in this parameter region. However, all the other homoclinic solutions reach a maximum value of beta 2 and falls back towards the negative values of beta 2. That means if you take a fixed parameter value, each homoclinic solution, there exists another homoclinic solution which is related, and both these homoclinic solutions going to coalesce at the maximum value of beta 2 where it falls. You can see it both in figure D and figure E. In this figure, we are showing another E to P connection, two distinct E to P connection in panel A and panel B for different periodic orbit than the what we shown in the previous slide. So as you can see, there exists two E to P connection. And if you look at the figure C1 to C4, all these homoclinic solutions are associated with the E to P connection shown in panel A, and they are symmetric. But most importantly, I would like to take your attention to panel D1 to D4, because up to now, all the homoclinic orbits we found are either symmetric or antisymmetric. But these panels show that not only symmetric and antisymmetric homoclinic orbits, we can find homoclinic solutions which are non-symmetric, and you can clearly see that all these non-symmetric homoclinic solutions are associated with the E to P connection shown in panel A and panel B. And as we did as before, we obtained the bifurcation diagram of both these symmetric and non-symmetric homoclinic solution by varying beta 2, and we can see that all these homoclinic solutions also reach a maximum value of beta 2 and falls back towards negative beta 2 values again. Up to now, it's clear that most of the homoclinic solutions fall as a certain value of beta 2. However, one could expect that these false points might change if we vary the other parameter values. In order to understand it, we find a relationship between the parameters at the fall point. The panel A show how the false points of some of the homoclinic solutions or orbits change in beta 2 and beta 4 plane. Here, the black dash curve corresponds to the Carlson and Hooke solution family, and it lies outside the purple color parabola, since it only describes the solitons with exponentially decaying tails. Panel A gives an overall picture in which quartic and quadratic dispersion values each of these multi-homoclinic solutions exist. In fact, it contains information of the existence of these homoclinic solutions when someone fix beta 2 and vary beta 4. Similarly, panel B show how the false points change in beta 2 and mu plane. It gives an overall picture in beta 2 and mu values. Each of these homoclinic solution exists. In order to get some idea about the stability of these newly obtained solitons, we integrate them as solutions of the PDE. Here we do all our simulation using the split step Fourier method. We take some of the solution we found and subject them to 1% perturbation and see how far these solution can stably propagate. Here we consider 2 and 3 hum solitons for different beta 2 values. As you can see, all these solitons propagate safely for some dispersion lengths and they start to repel. However, both the solitons we consider here, when beta 2 is equal to 0, which corresponds to the pure quartic soliton, they propagate stably than for other beta 2 values. Also, for most of the parameter values we consider here, they propagate more than 150 dispersion lengths. Therefore, although they look unstable, we believe that some of these solitons may be observable experimentally in photonic crystal waveguide. So uh, finally, I would like to make some conclusions. So we have found that there exist infinitely many symmetric, non-symmetric, and antisymmetric homoclinic solutions of the ODE, which corresponds to the soliton solutions, which corresponds to the symmetric, non-symmetric, and antisymmetric soliton solutions of the PDE, and we show that they exist in a certain parameter range as value. And as my future works, you saw that the importance of the PDD curve is to find the homoclinic solutions. Therefore, currently I'm working on the surface of PDD curves, as you can see in this diagram. Thank you very much.